this webinar, I show you the code coverage function that we provide in UDE and how it can be used to prove the quality of your tests. Before I start, let me give you a short overview of what you can expect from today's webinar. At the beginning, I will give you a brief introduction into the topic code coverage, with the particular focus on trace-based code coverage, how it's working and what you can expect. Then I show you the feature in UDE, the analysis functions in general, and how to use them in a real-life demo, and then we will have a look at the automation capabilities. That means how to embed the code coverage measurement in automated tests. So the debugger, especially our UDE, is not only a great tool to find bugs in your application or in your software, it is also a tool that supports you when you test your software directly on a real target hardware. For that, UDE provides a lot of features that help you to execute automated tests, and particularly the software API of the UDE that allows you to use scripts or for automated tests, or you can connect third-party tools to the UDE. This is a complete a whole topic, and I have addressed this already in previous webinars. So I'd like not to go into the details today, but if you are interested in this topic and you missed the previous webinars about automation, then please visit the Hitex YouTube channel, and you can there find the webinars about automation and scripting with UDE. So, now I'd like to start with the actual topics for today, with the code coverage in UDE. So you may know that a test of your software is not sufficient, especially in the field of safety critical applications. So if you are looking at the standards, for example, the ISO 26262 for electronic systems in road vehicles, or for example, the DO 178 for electronics in aviation, then you see that not only the test itself is addressed there in great detail, but also the evaluation and of its significance and the quality. So one of the metrics for evaluation of tests and for ensuring test quality is code coverage. So basically, code coverage indicates how much code was actually executed, triggered by the test cases by observing the code execution. So I'd like to show you this on a very generic example here on an illustration. Assuming you have a piece of software, this can be a function or that can be a complete module. And if you test this piece of software, you use test cases as an input, and you get an output, a test result. The input, I named it X, and the result, I named it Z. And the test is, while you execute the test, your software calculates with the test vector X1 an output Z1. In this case, it is okay, so the test has passed, but you see that with that single test case, you only triggers a subset of the whole function, or the whole or the module here. There is still code here that is not was not executed during the test. But the code coverage requests you that you execute the whole system or the whole software here, and you need a second test case, for example. And you see here, there is still code not executed, so you need a third one to get a 100% code coverage during your test. There are different levels of code coverage that are required by the different standards. The simplest one is the statement coverage, or sometimes CO, which gives you the ratio between the executed statements in your application or the executed instructions to all the statements or instructions of the module or function under test. This tells you nothing about the conditions in your code, of course, because you're only looking at the executed statements. To ensure that also all the paths in your application are tested for the different conditions, then you will need at least a branch coverage, or C1. This gives you the ratio between the taken branches compared to the overall number of the possible paths through your code or through your control flow graph of your application or of your module or function. And then we have the MCDC, the modified condition decision coverage. That is looking at the decisions. So the a decision means, for example, the condition given in a if statement in your code. And if you have more complex conditions or decisions that combine multiple simple or atomic conditions, the MCDC coverage requests that you have to ensure that each condition, simple condition or atomic condition in such a decision, independently of the others affects the outcome of this decision. This is a very complex thing, this MCDC coverage, and it is requires some precautions, and that's why I will not go into the deep details, because this you will see later that this is not possible with the trace-based approach that I will show you later on. So there are other tools on the market which are able to do or perform some MCDC coverages. Important here is that the code coverage tells you nothing about the software quality itself of your product. It tells you only about the quality of your tests. So your tests may fail, but you have a 100% code coverage, but you see, okay, you have good test cases. So how we do measuring the code coverage? Let's have a look at this simple example here. We have a code that returns the absolute value of an input X. If you want to do a test that achieves a 100% statement coverage, then you need only one test case. For example, X equals -7. And then if we execute this code, then you see that we executed all the statements here in this in this graph, and we get a 100% code statement coverage here. But there is a path that was not tested, and this is the fall through path, or sometimes also called branch not taken path here. And if we want to if we want to test this path also, then we need a second test case. For example, x equals 7, and with that we also triggers this branch not taken path. And with both test cases here, we get not only a 100% statement coverage, but also a 100% branch coverage. What we did here manually for measuring the code coverage and for evaluation the test cases regarding their suitability was that we executed the tests. We observed obviously the instruction flow in this control flow graph. So that means which edges of this control flow graph were executed, and then we calculated from these edge countings the coverage results. In the first example, the statement coverage, in the second test case, the branch coverage. So the question here is how we do this in the tool. So how we do the observation of the code execution. There are basically two ways to do that. First is we can instrument the code so that the code observes its execution by itself. There are a lot of test tools and verification tools on the market working like that. The great advantage of this approach is that you can do the tests at your PC running a simulator or something similar, and that means the tests are completely target independent. Target means the real hardware. So there is no limitation regarding the code coverage levels. I mentioned that before, that with the approach that I'd like to show you in a minute, MCDC coverage is not possible, but here for the code instrumentation approach, also MCDC coverage is possible. But if you change to real hardware, then I guess you get some undesirable things. Because of the code instrumentation, the runtime behavior is changed. The reason is that you add some code here to instrument your application for the testing to observe the execution of the control flow graph, and that needs time, and so you change the runtime behavior. Then you get a changed code size as well, obviously also by the instrumentation, and possibly you get a different memory layout because of the data that has to be collected during the test and during the coverage measurement and the observation of the runtime during the runtime. At the end, you have to be aware that the code under test with instrumentation is not that code that you will use later in the field in your product. The second approach gets the data for calculating the code coverage by using trace. Trace is a hardware feature of almost all the microcontrollers on the market, which allows you to do a complete non-invasive observation of the runtime behavior and the code execution. You need no code instrumentation, and so there is no influence on the runtime behavior. So the code under test is the same code that is used later in the field. But this approach has also some disadvantages. The approach gives you only the coverage at object code level. That means the machine instructions, because the trace observes the executed machine instructions and not has nothing to do with the original source code. But in my opinion, this is not a real disadvantage, because you get the coverage for your tests that are executed on the real code that is mostly optimized by the compiler and which is also the final product code. The real drawback is that in some specific cases and with highly optimized code, you will miss some information about the control flow inside the code, which may lead into incomplete coverage results. And there are solutions for that. Because of the time, I will not cover these solutions in this webinar, but there are compiler extensions available that uses debug information and adds some important information into the debug information that the debugger and the trace system can recalculate and reconstruct the control flow that are lost by the optimization steps, because these debug or these additional information are part of the debug information. The binaries are not touched, so not changed, so there is no influence on the runtime behavior by that. But the results of the code coverage are correct again then. And as said before, MCDC coverage is not possible here by using or relying on trace, because the complex decisions are broken into simple branches by the compiler, and for that a MCDC coverage makes no sense anymore. If you need MCDC coverage, then code instrumentation is the way you have to go. A last statement here from my side is it's very important to understand that we have a limited amount of trace memory, either in the target hardware or in the tool, because we need a hardware tool to capture the trace, which needs to be implement some trace memory. And this trace memory is always limited, and in the typical use case of trace-based code coverage, you have to test the functions one by one and then accumulate the code coverage results. And I'll show you that later on how it works. So then it's time to have a look at the code coverage feature in UDE. We provide a trace-based code coverage there in the debug tool UDE that can calculate two levels of code coverage: statement coverage and branch coverage. We present the coverage results in the tool itself in a dedicated code coverage window that has or provides you a compact presentation of all the results in different levels. So because we do a object code coverage, we have not only the function level, the high level language level in C or C++, but also the object code level here to present the code coverage results. Then, of course, you need reports to document your tests and to document your achieved code coverage. That can be also created from the calculated code coverages in UDE and output in different formats. And we have also functions that can be used to access the code coverage For automation, we provide a software API to allow access to all the coverage features and to couple scripts or third-party tools to the code coverage function of UDE. But this will be addressed later on in the last part of this webinar today. As said before, UDE is not only an interactive active tool. No, that's okay. Now it's time to jump to the UDE. So I was a little bit too fast. So let's jump to the UDE, and I'd like to show you how it works interactively, and then I'd like to show you how it works in a automated test session. I have already opened the UDE and loaded a workspace, so a debug session, and already loaded a application that should be tested into the target hardware. In that case, I have an RX here on my desk. And the application that I'd like to test is a simple clock. So the simple clock counts the tens of seconds, the seconds, of course, minutes and hours, and the main routine for updating the clock is this core1 update clock function here. So this is executed by an interrupt every 100 milliseconds, and every 100 millisecond we like to count up the tens of seconds, and then if they are wrapped around, then we update the seconds and increment the seconds, and if the seconds are wrapped around, then we update the minutes, so we increment the minutes, or if they are wrapped around, then we update the hours and so on. Quite simple, and we want to test this function here. So let's start this application. You see here in the watch window, I have browsed in the variables of the clock here, and we want to test them. So I can use, for example, the watch window to change the values here and to input some test values, and in parallel of that, we want to do the code coverage. To perform the code coverage, I need to firstly to set up the trace system. So we need to configure the trace system that the trace is recorded, especially for these functions that I want to test. And for that, I use the configuration tool, which we call UAC in UDE, which is a graphical configuration tool that allows you to compose a trace task based on some predefined subtask that is given by a library here to a complete trace task. And this is very simple here in this case, because we want to test the functions that are running on core1. I have to select core1 to be observed by the trace system, and then we want to perform the code coverage for all the test cases that we input here manually in the watch window. And for that, I use the so-called pre-trigger setup. The pre-trigger setup is, in this case, works as follows. The trace is started, and at a certain event, which we have to specify in a minute, and then the trace runs as long as we have enough trace memory available. And now we need to specify what should be traced, and in this case I'd like to trace everything in between this core1 update clock function. So if we enter this function, then the trace should be started, and if we leave, the trace has to be stopped until the next core1 update clock cycle is executed, and then we start the trace again and stop the trace if we end that. So that we observe a lot of these functions here, and also the functions that are called the sub-functions. So we start the trace at the core1 update clock, and we stop the trace if we leave the core1 update clock. This can be done with this end off here. And then we are finished, and then we can start the trace and start the recording of the executed core1 update clock function. We start the trace, and then the trace is recorded, and we can, for example, input some values here. For example, we change the seconds to 59 and force the wrap around, so we see the minutes are incremented, and because we have not too much time here, I stop the trace here and look at the code coverage results that we have achieved here. And we see, if we open here in the code coverage window, the core1, and we see all the functions that has been triggered by our test case, and we see the coverage results here as a bar chart, and we see, okay, we have some statement coverages, which is this column here called line coverage, because we do not focus only on C statements, but also on assembler statements or assembler or machine instructions here. That's why we call it line coverage. And then we have a MCB coverage. That means this is a machine code branch coverage. And here you can see the results of your coverage. So you see that we have only a partial coverage of the update minutes function here, 70% statement coverage, 50% branch coverage, and then you can look into the details here, which lines of source code has achieved which amount of coverage here. You see, we never tested the minutes wrap around here in this. That's why we get only a 50% branch coverage, and then you can look at the details here by opening the different lines and see also the assembler statements here. From that, you can also create reports manually. You can select different types of report outputs. You can browse for a folder where it should be saved, for example, that one. And then you can also define a file name for all the reports based on predefined variables, for example, the module name, date, time, etc. Then you can press OK, and then you get the report for all the modules that were traced here. So there are 2 modules that are traced, and then you get all the results with the starting from the functions, and then you can go to the lines and also the machine code instructions. Okay, but this is not the typical way you do the code coverage. The typical way is that you do not use the code coverage too interactively. You do the code coverage instead together with automated tests. And I said before that the UDE can be embedded in complete test environments. You can do this by scripts, or you can use UDE together with test tools. And for both, we provide a software API that we call object model or automation interface. And with that, it is possible to do a kind of remote control of the UDE. So you can control the application on a real target device by your script or by the test tool. You can write test cases into the hardware, and you can retest results, of course, and then you can in parallel capture trace information to calculate the code coverage that you achieve with your tests. Because of the time and because there are webinars also available about the object model, I will not go into the details of the object model, but a few words about that. The object model in UDE is composed out of a set of objects, as the name says. The objects provide interfaces that give you access to almost all the debugger functions. And if you look at this picture here on the left side, you see that this is a hierarchy of objects. So we start every time at some topmost objects, and each object provides properties or functions that allows you to obtain the lower level objects in such a hierarchy here. The topmost objects provide you the functionality either to connect to a running UDE by your script, for example, or to open a new UDE and create a new debugger session or test session. And from that, you use the so-called UDE application object and obtain all the other things you need for your testing, including the trace objects that provides you functions for capturing trace information, also for the code coverage analysis. So, and this I will show you also on a real example here. I have prepared already a Python script in this nice Jupyter notebook, which is a web-based or browser-based application that allows you to interactively write Python scripts and execute based on such a cell parts of this script. And this is a very nice tool to show you how a Python script is working together with UDE. I clean up something. And for using this script for testing the application automatically, I'd like to change the trace configuration a little bit. As follows, because we want to do the test a bit different. We want to set a breakpoint at the beginning of core1 clock, update clock. And after we hit the breakpoint, we want to inject a test vector or a test case. And because of this breakpoint, we do not need a starting point for trace, but we need a stopping point for trace. So I changed the trace configuration a little bit so that we stop at the stopping point here, and we need a trigger event to stop the trace. And the trace recording starts as soon as we start the trace system on the target by the script. And we do not want to specify a specific code label or address here of our application, but we want to make the script or the configuration a bit generic. So we use a variable here, for example, start trace, and then we save the task here. I have already prepared that, so I cancel that, and then we can close that. Okay, and then we can start with scripting. So the first thing we do is some importings in what we need, libraries that we need for our Python script. We connect to a running UDE by the UDE running instance manager, and we do that. So we get the version information of the UDE. Then I specify a workspace directory that we are using later for the outputs of the recording of the reports. Then we connect to some of the debugger objects, the workspace, and also the debuggers of the several cores here. And we make sure that the application is running by this core 0 .go, and then we set the breakpoint. So the breakpoint is set and the application hits the breakpoint, and then it's time to prepare the trace. We obtain the trace object here, the UAC object, and load the saved trace configuration, which we named trace for code coverage.gtq. We then have to set the variable that we specified. We had named it stop trace, and we want to stop the trace at the end of core 1 update clock. We set this variable, and then we configure the trace. And then we obtain the code coverage object here. That should be that is the so-called trace use case object, which is parameterized by the function code coverage for core 1. And then we can set up the code coverage functionality. The first thing I'd like to do is, because we have already a code coverage here, a result here, that we clear it, and then we set up the code coverage feature to accumulate multiple runs of the code coverage, and that the code coverage is automatically calculated after the trace has been stopped. So we set the manual control to false. We see we have cleared that, and then the system is prepared for the test. So now we need the test vectors. For that, I define a structure of a test vector and also a good vector for the comparison. And then I define a test case. That is the test case of the minute wraparound. So we set the tenths of second to 9, the seconds to 59, and then the minutes and the hours to a value, a random value maybe. And the good vector, we expect that the tenths of seconds are 0, the seconds as well, and the minutes are incremented here. So we run this, and then we write these test vector, the first vector here to the target. You will see it in the watch window here. The values are now updated, and then we can start our test. We start at first trace, then we start the application and wait for the next breakpoint hit here, and then we check the values, the results. So we wait for the target halted. This is already done, and then we read all the values here of our clock and compare it to the good vector. And okay, the test has been passed, so the minutes are incremented and the seconds are reset to 0, and then we can clean up everything. And that's all. We get a code coverage result here, which shows us that we have only completed the core 1 update clock or tested the 1 update clock, because there are nothing to do here, but all the other functions are tested incompletely. So we need some more test vectors here and do a test loop. I have already prepared that. The script is slightly changed. The first part is everything from from getting the running instance, obtaining the workspace, obtaining the core debuggers, starting the application, and also setting the breakpoint. So we at the breakpoint again, and then we define again the test vectors here, like we did before, but we provide now a number of 4 test vectors for the corner cases in this kind of array here. And then we load again the trace system, the trace configuration, setting the stop trace condition, and then we configure the coverage again as we did before, and now we can start the test loop. So we have a loop of where we execute tests for each of the tests in the test vector, writing the variables, starting the trace, starting the application, rating that the trace has been done and the code coverage has been done, and then we check the results at the end. And if we are finished with that, we start again for the next test. I can execute this. And then we see, okay, we hit the breakpoint, we get some results here, we accumulate the coverage results, and at the end, now we are finished, you see that we have a coverage result which is not good enough because we didn't have a 100% coverage for the update seconds function. Now we can look into the update seconds functions and see why we don't have a 100% coverage, because this is because of this check here. And we see, if we are looking at the machine code instructions, that the branch coverage of this jump has only achieved 50%. And the reason for that is that the increment of the seconds was not tested by our test cases. So if you look here, we have no coverage for this statement here, and we have to add a new test here for the increment. I copy this test case, and then we want to check the increment, which is which we expect that we increment the seconds here, and then we execute this again and also the test again, and hopefully we will get a 100% code coverage here in this test case. Okay, test has been finished, and we get 100% code coverage, line coverage, or statement coverage, and also 100% branch coverage. And now it's time to save or create a report. We have also API functions to do so. We specify that it should be a HTML report. We specify the file name pattern. We did this already in the interactive session, and we want to include also source code lines in the report. And then we can save it, and it's opened automatically, and you see the results here in this report. Okay, time is over, and I'd like to finish this webinar for today. And yeah, I hope you enjoyed it, and I'd like to thank you to all of you